Hello, everybody. We're back. Glad you could make it. Uh, Today, we're actually starting on a series of four lectures. This module is four lectures, which we survey the different kinds of biological molecules, starting with carbohydrates, and we'll move into proteins, nucleic acids, and lipids. In a lot of ways, there's going to be some review because in the past, in last week's lectures, we went through the basic discussions of what the different kinds of molecules look like when they come together. For example, we'll be reviewing today what monosaccharides look like, and that would basically be review of their functional groups, their characteristics, and also the process of dehydration, synthesis, and hydrolysis that are important for building up larger molecules and for breaking apart the larger molecules to regain access to the smaller molecules, which are really important. Monosaccharides are important for us in a lot of ways. They are, if for no other reason, glucose, which is a monosaccharide, that would make on its own monosaccharides to be among the most important molecules that we'll talk about. We get practically all of our energy through glucose, as well as other monosaccharides. Okay, and so very important molecules. We are going to focus on just some things we haven't had a chance to talk about yet. Okay, and like I did in the last video, we're going to go through the content in the textbook first. Got to find it. Okay, here we are. Monosaccharides are the simplest carbohydrates. And so monosaccharides, they've got this structure. This is what I wanted to show you. I got to get my annotate tools out and drawing. And what you can notice here is that in these molecular diagrams, we're actually looking at two different kinds of monosaccharides. Glucose is one version, fructose is another. Okay? Now, here's the thing. If you look at them, you would count up 6 carbons in each. Okay? Carbon 6. And if you look in each one of these things, you would get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 hydrogens. Okay? And you would get 6 oxygens as well. Okay? C6H12O6 is the formula for both glucose and fructose, right? And so same formula, 2 different molecules. You can see that they're different molecules because the arrangement of the covalent bonds is different, okay? And so we would call these different isomers. Okay? And in fact, a lot of the diversity in organic molecules comes not from different chemical compositions, different atomic compositions. Differences like that between glucose and fructose is due entirely to the way that the covalent bonds are arranged. We still have the same set of 6 carbons, 12 hydrogens, 6 oxygens coming together, and whether you're glucose or fructose, all that matters is whether that carbonyl carbon is here or whether it's at the start of the number 1 carbon, right? And so there are little differences like this that organic chemists will make a big deal out of. I don't think it's that important, but it's a good idea for you to know that we've got lots of different kinds of molecules, both of which, all of which may have the same chemical formula, right? You could also have different sugars that are based on different numbers of carbons, right? So if you have 6 carbons, you would call that a hexose sugar. Sugar, because a lot of these things are sweet. Hexose means 6 to 6 carbon sugar, right? If you were to have 5 carbons, you would call that a pentose. Okay, sugar. And we're going to be having enough opportunities to talk about pentose sugars when we get into the structure of mononucleotides, right? So sugars can come in various sizes. Monosaccharides, individual sugars can come in various sizes. Glucose and fructose are a couple of good examples. Now, another thing that you want to note here, though, is that when you see glucose or fructose depicted in the textbook, you're not going to see them as a straight chain like this. You don't get to see the number 1 carbon at one end and the number 6 carbon at the other end. No, this is actually a very nice depiction, but it's not the way that they occur in reality. And so when you actually draw the carbon out the way it occurs in solutions, it's a little bit more stable when it forms a ring shape, right? And so you can call this the ring forms of glucose, and that would be okay. And I think I've done this with you before, which is that we can use the full glory. This would be the full glory picture of all the carbons, hydrogens, and oxygens in glucose, right? You could abbreviate that by showing just the things that are coming off the side, and these corners that I'm drawing in are understood carbons, right? The number 1 carbon is right here, 2, 3, 4, 5, and 6. Those are the 6 carbons, and so you don't actually see all of the C's there. And you know what? That might also be too much work, right? To draw. And so very frequently we would just draw a little hexagon in which we show the members of the glucose ring, the 5 carbons in the glucose ring, and the oxygen. And this is what the book's identifying as a simplified structural picture. So when you see long strands of hexagons, you should get used to the idea that that's not just a strand of hexagons. Each hexagon represents the molecule that drawn out in its full glory, but like the structure that we have over on the left. Okay, and that's the part that we are thinking about at this point. Clear my drawings, go back to the mouse, and I think we're going to be moving into the next topic, which is also going to be a review. Oh, well, yeah, just one more thing, right? This is a good opportunity for us to just review in our minds, what does it mean? What does it mean for us to have OHs? Okay, lots of OHs. Are monosaccharides going to be hydrophilic or hydrophobic? What do you think? Yeah, well, I'm hoping you're going to say, well, these are, as you can recognize, OH bonds. These are polar covalent bonds. There's going to be a delta minus on the oxygen side, delta plus on the hydrogen side. Every time that you have an OH, you'll have a delta plus and a delta minus. And so these are molecules. Anytime you see all these OHs, these are going to be molecules that will interact with water relatively readily. And that goes along with your general experience, right? Glucose and fructose are both highly soluble in water. You mix them into your coffee. High fructose corn syrup, glucose, common form of glucose would be caro syrup, corn syrup. Okay, so that's all that we needed there. And so now we're going to be moving into the next part of chapter 3, which is going to be talking about the way that 2 monosaccharides link together to form a disaccharide. And again, this is going to be a review. So we're not going to belabor this. We actually did this in detail in the previous lecture. We said that, yeah, when you look at the glucose, these are glucose molecules drawn out in full glory. There's a water molecule that comes out. This process going in the downward direction would be dehydration synthesis or hydrolysis. Yeah, this would be dehydration synthesis. One, because water is coming out, right? And 2, synthesis. Remember, syn means together. We're bringing together the 2 glucoses, right? And so glucose 1 would be a monosaccharide. Glucose 2 would be a monosaccharide. At the end, we would get a disaccharide. And when you have 2 glucoses that are hooked up one to another, a very common form of that would be the disaccharide, the sugar called maltose, right? Which is malt sugar. If you've ever brewed beer, right? You know that to brew beer, what you do is you start off with some kind of starch, like barley, and then you have to apply an enzyme, or the barley has its own enzymes, so you don't need to apply a new enzyme, but activate the enzymes, and the enzymes will break the starch down into sugars. And the sugar you end up with is malt sugar. And malt sugar is simply two glucoses that are hooked up end to end, right? So that's a disaccharide. If instead of having a glucose and a glucose, if you had a glucose attaching to a fructose, that was the sugar that we looked at in the previous section, that would give rise to sucrose. I mean, that sucrose is a disaccharide that is resulting from the hydrolysis, the dehydration synthesis of a glucose with a fructose molecule. It's also table sugar. So granular table sugar, either cane sugar or beet sugar, one that we use most typically in cooking, mixed into coffee, etc. That's sucrose. Another disaccharide would be glucose and galactose. Galactose is another hexose sugar, 6-carbon sugar, and that would give rise to the disaccharide we know as lactose. Okay. And so lactose is milk sugar. And when somebody says they're lactose intolerant, all that means is that they're not able to break the disaccharide down into glucose and galactose, the monosaccharides, which has to happen before you can absorb those nutrients, right? And so if you can't break down lactose, then basically lactose goes on and feeds the bacteria in your gut, which causes you to have the discomfort. The resulting byproducts like carbon dioxide gas are the outcome, are the consequences of the bacteria breaking down the sugars that you're not able to break down, right? So there's that. And so, yeah, I guess the idea is that we talked in the last section about the idea that we've got a huge diversity of different kinds of monosaccharides based on the number of carbons that are there, based on whether they're forming rings or chains, and also based on the arrangement of the covalent bonds. And like glucose and fructose were different isomers of the same chemical formula, C6H12O6, right? What I'm telling you now is that you have a diversity of different kinds of disaccharides, because if you've got all these different kinds of monosaccharides, you can put the monosaccharides together so they're two of the same. You can put them together so there's one of these and one of those. And the different kinds of disaccharides are going to differ based on their composition from their component monosaccharides. Okay. And so we use, honestly, I don't think it's terribly important for us to talk a lot about disaccharides, although they do come into our consciousness quite often, right? Malt sugar, table sugar, milk sugar are things that we're used to. I guess for me, another big instructional point is that we're seeing the connection between monosaccharides and larger structures. So if you were to take this theme of glucose coming together with glucose, dehydration synthesis to put together a disaccharide, in your mind, you should be able to continue that, maybe putting on another glucose over here on this side and adding another glucose on top of that. And eventually you'll end up with a big long strand of glucoses hooked up end to end. All right, and that would be a polysaccharide. Next part of the chapter is this little bit of nutritional information. Go ahead and read that. Are we eating too much sugar? Yeah, probably. Yeah, not our main focus right now. We're thinking about biochemistry, molecules. Right? And so here's another way in which I can illustrate. You already have the idea that polysaccharides could simply be one glucose hooked up to another glucose, hooked up to another glucose, hooked up to another glucose, and you could have this long monotonous chain of glucoses hooking up end to end. And if you did that, you would end up with starch, right? So starch is a monomer of glucose in which you've got a particular kind of end-to-end linkage such that you get this kind of coily shape. Okay? Glucose forming long coiling chains gives us a starch molecule like what you find in potato starch. If you have a little bit of branching, that might give you arrowroot starch. Corn starch might have more branching. Different kinds of starches have differing amounts of branchiness, right? And so if you have an extremely branchy version of glucose, glucose polysaccharide, you can get glycogen, right? And so starch is what you find in plants. Glycogen is the polysaccharide of glucoses that you would find in either your muscle or in your liver, right? Basically, these are large storage polysaccharides where you could store your glucoses because you just ate a whole bunch of French fries, and you can keep those glucoses. You don't need all the glucoses right now, but you can store them and access them later on when you haven't been eating so much, right? And so yeah, these are polysaccharides of glucose. Another kind of glucose polysaccharide would be down here, which we're seeing in the case of cellulose, right? So cellulose molecules, it's another form of glucose polysaccharide, but the chains are straight, not coily, right? I don't know if coily is a word, but you know what I mean, right? We don't have these coily helices forming, and because they're straight, they tend to stack up, and we can stack them really tightly to create long fibrils, like little threads, little sturdy threads. And these are things that we use to make a structural molecule like what we find in plant cell walls, right? So plant fiber, the things that holds the cells together, is also made of a glucose polysaccharide, only it's put together in a different way that allows them to have a structural function as opposed to a storage function, right? And so right there, we've pretty much covered the entirety of the functionality of different kinds of carbohydrates. I mean, carbohydrates come in monosaccharides, disaccharides, and polysaccharides, right? Monosaccharides are important because they're the form of energy that our cells will be using. We'll talk about that in our next unit. It'll be like the first thing we cover, or one of the first things we cover in unit 2. Okay, now the second thing we do is we have to store monosaccharides. And we do that both in disaccharides as well as in polysaccharides. And so a storage molecule like the glycogen in your liver are going to be able to release glucose later on during times in which you're not eating. When you eat a big meal rich in starch, you can store the extra glucoses there in the form of glycogen. Starch is done for the same reason for plants, right? A potato stores glucose as it's producing today. It stores them away in big starch molecules in its tuber, and later on, when the plant is going to be needing to access those starches to grow big and strong the next year, it'll be able to mobilize those starches and provide energy and raw materials for the growth, right? Similarly, the plant might be producing glucose and putting them into some type of structural molecule. Okay, I made this L look like a T, so it's bothering me, so I'm going to erase that. A structural function as opposed to a storage function, right? And so, yeah, these are two different ways in which glucose molecules can be put together. Now, there's one more way that's important. I'm going to go back to my original share here, whiteboard. And that is in these, kind of capitalizing on some of the things we've talked about already. The idea that we've got many different kinds of monomers, right? Monosaccharides. Maybe it's called the monosaccharides A, B, C, D, E. There are dozens of different kinds of monosaccharides that differ in subtle ways, right? And so if you think about the different combinations, the different ways in which you could put together A, B, C, D, and E into different chains, let's say we have a chain of 10 monosaccharides, right? You could put them together A, D, C, B, A, E, E, A, C, C. I mean, this could be one combination. There are, bazillions of different combinations that you could make from the 10 monomers. And if each one is going to have a different identity, right? This short polysaccharide this specific sequence of A, D, C, B, A, E, E, A, A, C, or ACC could be used as a cellular identification tag. And in fact, this is actually one of the ways in which polysaccharides are used. The cellular markers, there are many ways that cells are able to recognize what kind of cell they're bumping up against. And one of the ways is to have molecular markers on the surface of cells. One of the major kinds of cellular markers are these short polysaccharides that differ in the sequence of monosaccharides that are on the surface. Each cell might have its own distinct cellular ID tag, which will allow other cells to recognize what kind of cells they're dealing with when they bump up against them, right? So review time, monosaccharides, from a chemical standpoint, they have hydroxyl groups, they have a carbonyl group. We care mostly about the hydroxyl groups because we want to think about monosaccharides as being totally recognizable as being hydrophilic and water-loving, right? We know that they're going to be appearing as images in their ring form, not their chain form. And those are going to look like little hexagons, often with an O in them. If you have an O in a ring, you can pretty much bet that it's going to be a monosaccharide, right? We also know that their general formulation is going to be about an equal number of carbons and oxygens, about twice that number of hydrogens. And so if you're looking at a big molecule and, hey, it looks like I have quite a few oxygens, looks like the oxygens are about equal in number to the carbons. And you know what? I also have hydrogens that are about twice as many as either the oxygens or the carbons. You should be able to recognize that as a carbohydrate, right? And you might even be able to recognize the structure of many rings that are hooked together, right? But if you can't recognize the rings forming a chain, you can at least see that you've got a whole bunch of O's to go along with the H's and the C's, right? Most other kinds of molecules are not going to have as many oxygens on them, right? We reviewed dehydration synthesis and hydrolysis as mechanisms by which monosaccharides get together to form disaccharides. Disaccharides would be doing hydrolysis. I didn't really show you that, but you could just reverse that reaction to hydrolyze a disaccharide into monosaccharides. We talked about polysaccharides and how they could be used for storage, starch in plants, glycogen in animal cells, or for structure. And cellulose was a good example of that. One of the bigger differences between kinds of polysaccharides, different kinds of starch, difference between starch and glycogen is the amount of branching that's there in the chain. Some will be more or less straight coils without a whole lot of branching. Some will be coils with branches and more branches, right? So if you have a big branchy coil like that, that's going to be a different molecule compared to that, even though they're both made of long polymers of glucoses, right? And the last thing, we talk about this in the very last module of the semester, we discuss cellular identification in the immune system, is the way that this diversity of different kinds of monosaccharides could be used to create cellular identification markers, okay? And that pretty much covers everything that we need to talk about in the context of carbohydrates.